I basically wanna start where we left off yesterday. So a little bit of a reminder for what the context is and what we want to do today. I first want to start talking about generic maps of the plane. And then we'll use that a little bit to build towards the Tom Boardman stratification. And then we'll go from there. The thing that I want to remind you of is that if you give me a smooth map from M to N, we define those sets SRF. So these are the critical loci of points in M where the differential of F drops rank by R. And we also define these smooth submanifolds SR of the first jet space from M to N, which again consists of those jets where the differential of the germ drops rank by R. And the definition, which I don't think I gave yesterday, but it's a fairly simple definition, is that if you give me a smooth map, this map will be called one generic if its first jet section, oops, that's not what I wanted to do. Its first jet section intersects these SR submanifolds transversally. So for example, the Morse functions are the one generic maps with target R. And also we saw yesterday, we talked a little bit about immersions and basically saw that those are the one generic maps with targets of high enough dimension. So, and again, recall from yesterday that those sets SRF can actually be identified as the pro image of the first jet section of those SRs. So this is a little bit of a typo, sorry, J1. And so in particular, if our map is one generic, so if we know that if we have all of these transversality conditions, we know that the sets SRF are actually submanifolds of M. This is the transversality theorem that we saw yesterday, not Tom's generalised. And also, when the target is one-dimensional Euclidean space, this basically contains all the information that we may need. So if the target is one-dimensional Euclidean space, this almost completely characterizes the kinds of singularities that we have. We know that all singularities of F or critical points of F will be in S1 of F. This doesn't require any transversality to see. It just follows from the fact that if your target is one-dimensional, then you can only drop rank by at most one if you are a differential of the map. And the thing that does require and did require transversality to see is that if J1F intersects S1 transversally, then those critical points are all non-degenerate. So that's what we saw yesterday. Do you know where Bruce went, or shall we wait for him a little bit, or? Okay, so yeah, but the problem is that this is no longer going to be the case if the target is R2. So I want to give two examples. Might actually be better if I stop for a second to let Bruce. Okay. So yeah, I just to wrap up. So I said that if the target is one-dimensional, then knowing, like being one generic, having this transversality condition would completely determine what types of singularities that I have. But I'm just about to like give an example for why this is no longer going to be good enough if the target is the plane. So so here is like two maps. Well, I guess let's start with like one map from the plane to the plane, from R2 to R2, which sends points x comma t to x squared comma t. So you can think of it as like having the graph shown here. What is the differential of this map at x comma t? So I guess I can think of this map as being composed as being I guess two maps corresponding to the two coordinates in the target. So I don't know if this is f1 and f2. And here I'll take the partial derivatives of f1 with respect to x and with t. So that gives me 2x 0. And here I'll take the partial derivatives of f2 with respect to x and t. So that gives me 0 and 1. So in particular, we see that the differential is going to drop rank. It's going to drop rank by 1 for all these points in the plane when x is 0. And that's our locus S1F. So S1F consists of the line corresponding to just the t coordinate axis. Okay. And I don't have any points where the differential is going to drop rank by more than 1. And well, is that clear? Or, okay. So another map that I can write from R2 to R2. This is map G, and it sends x comma t to x cubed minus tx comma t. So what's the differential of this map? That's going to be well, 3x squared minus t minus x 0 and 1. Okay. So this differential is going to now drop rank at all points when this here is 0. So it's going to drop rank at all points in the plane where t equals 3x squared. And that's the S1G locus, consists of all those points of the form x comma 3x squared. It's like a parabola in the plane. Okay. And again, I don't have any points where the differential is going to drop rank by more than 1. Is that
because you got a 0, 1 column?
Yeah.
Okay.
Exactly.
Okay.
Exactly. So both of these, like, you know, like both of these functions, in terms of the theory that we have developed so far, it's quite hard to distinguish between them. Like in both of these cases, you have that the S1 locus of the function is a one-dimensional submanifold of the source. And like all critical points are critical points where the differential drops rank by 1. And we don't really have much more that we can say, even though we would want to be able to distinguish between them.
Let's ask the question here. So just go back to the definition of one generic. Okay. So let's ask the question if these functions are one generic.
Yes. I won't give you a proof, but I claim that they are. So yesterday we saw how like being one generic implies a non-degeneracy condition. But we did use quite crucially in the proof there that the target was R. Yeah, and here here the target is R2. So these are actually like they both would be they would both be transverse to S1, the first jet section.
Let's just make sure that Daria and Kolile are with us, so that they're welcome to interrupt at any time.
Yeah, thank you, Chris.
Okay.
Yeah.
Cool.
Yeah. Sorry, let me make sure that all participants can have the right to speak. So allowed to talk and allowed to talk.
There's Ken Hughes. Hi, Ken.
Hi there.
Okay, and good to have you here. And Tekiso, hello. Okay, that's fine.
Okay.
So I still don't get like, because what are these telling us, like, so this example, what are they telling us? The information that we are getting is what is different from the one with the target of R.
Well, so when the target was R, I guess we had this condition of like being one generic. So when the target was R, basically we had that everything, like all the critical points locally would look like would take this form. They would be this, like, they would have this quadratic form. And that was like completely determined by like this one genericity condition, and also by the fact that you had all I'm trying to say is that here this wouldn't be enough to distinguish between everything we might want to distinguish. And it's kind of like, well, in some sense, it's not hugely surprising because we only work with the J1 bundle, and like these two functions here, I mean, like to see their difference, you would have to go up to like the 3-jet space. That's where you would detect that they are different. But it's still a question. There's still a question of like in what form are we going to get to the 3-jet space? Like, what should we ask in order to be able to detect the difference between these two functions?
I agree. But then there's a more basic question, which is just, so for functions on a manifold into R, we know that being transverse to the one jet, or that the one jet of F is transverse to S1 is equivalent to the critical point being non-degenerate. For functions to R2, it would be nice to have a characterization of when the one jet of F is transverse to the S1.
Yeah.
Yeah.
We'll get something.
Okay.
You'll see how it's you
Okay.
get something maybe a little bit even stronger than that. So I think yeah. Yeah, hold that thought and we'll get it in a bit. So yeah, so basically, I'll carry on with this example because it's a nice example to see in detail. And the thing that we will exploit is that S1F and S1G are submanifolds of R2. So that's something that I guess we can kind of see. We will exploit that. So in particular, one thing that we can do is we can take the original function, say F, and restrict it to S1f. And also do the same, take the original function g and restrict it to S1g. So now we get like a new function, and we can try and see what the singularities of that will look like. Okay, so if I do that, I look at f restricted to S1f. So that will now be a map from R to R2, and it's going to send t just to, well, 0, t. Okay, that's what's going to happen. And then the differential of this map is now just going to be just 0, 1. So it will never drop rank. Okay. Whereas if I do the same for G restricted to S1G, now I will again get a map from R to R squared, and this map is going to send X to, well, maybe I should, well, I guess it's going to be a little bit hard to fit everything in the same page, but it's going to send X, if you look at the formula here, to X cubed minus 3x cubed, comma 3x squared. Okay, because t for us is going to be 3x squared. Okay, so what is the differential of this map? The differential of this map is going to be, well, this here is just minus 2x cubed, so we get minus 6 x squared, and we get 6x. That's the matrix that's going to give us the differential. So in particular, now this map here, the differential is going to drop rank by 1 at 0. So this is where we now detect a difference in the behavior of the critical points of those two maps at 0. We couldn't really detect this difference previously. Both of them, just their differentials dropped rank by 1. But then when we pass to the critical locus and restrict the function there, this new function studying that gives us a difference between those two critical points.
It's very interesting that there's this sort of subtlety goes on here. Okay.
And I think it is related to the question that I think you've been having throughout, is like, so because maybe, well, actually, let's keep that thought for what I'm about to say, and then so this is the motivating example, at least in my head, for building up what's called Tom Boardman theory. So I want to pose, if there are like any questions about sort of like what we kind of did, or like or if everyone is on board.
You could draw a little picture of the vectors, you know. So on that red graph there, or you can draw a little picture of the direction in R2 for which the function drops rank, and somehow the idea would be that where you're dropping rank is sort of transverse to the submanifold S1 here.
Yeah, it's basically, yeah. I mean, one thing that I should have done actually is I should just identify in those pictures what the loci of the critical points are, right? So
yeah.
I guess here, this is what the critical points, this is the loci of the critical points in this graph. And I mean, take these pictures with a grain of salt, because the critical points actually live in the manifold,
yeah,
and here I'm
yeah.
just showing you like the graph of a map. So
That's fine.
so this isn't
Yeah.
but maybe just like
Yeah.
to get a little bit of intuition. And then here is like another like loci of critical points. So in R, if you look at what's happening in R2, or I guess if you look at what's happening in R2, in the left-hand side, you have a manifold which is just the t-axis, and then in the right-hand side, you would have a manifold which is just this parabola, and then when you restrict in this parabola the function takes a form where you can see that the differential is going to drop rank at this point.
But you can actually draw at each point the direction in which you drop in rank, and the idea is that on the left hand side the direction would be sort of perpendicular to that brown line. On the right hand side it will also be vertical, but that will be tangent to the brown line at that point. Okay.
So I just want us to take this example, have it in our heads, and get a bit of a view of what Tom Bodmer theory does. So I'm saying that suppose that I'm given a smooth map, which is one generic. Okay, so being one generic means that all these submanifolds, all of these initially subsets of M where the differential drops rank by R are actually submanifolds. Okay, and so we can now define we can define subsets of those SRFs, which I'm calling, I guess, S sub R comma S of F, and these are going to be the loci of points in SRF where the differential of F restricted to SRF drops rank by S. Okay? So in the above example, just to see how this definition maps into the above example, if you look at the I guess right-hand side function, which had the cusp, the point 0, 0, that lives in S1, 1 of G, right? Because the differential there drops rank by 1, and then restricting G to the locus of critical points, there's a new function, its differential will drop rank by 1. And then all other points of the form x, 3x squared, apart from 0, 0, they live in S1, 0 of G. And then for F, S1, 1 F is empty, and S1, 0 F consists of all points in S1 F. So just the entire t-axis. And that's now basically, I guess the motto is that, we had these subsets SRF, and they made us introduce this strata in the first jet space. And we are going to proceed very analogously. So we are going to do the analogous thing in the second jet space for these subsets as R commands. So the story basically goes as follows. It's for each of these submanifolds SR in J1 of M comma N, I basically want to look at, I want to pull them back to the second jet space. So I have this map from the second jet space to the first jet space that just forgets the 2 jet information and only keeps track of the 1 jet information. The SRs live here, and I want to take the I just want to take the pro image in the second jet space. Okay, and this thing is what we will now stratify. We will introduce submanifolds of this thing, which we call S R comma 0, R comma 1, R comma S. And the guiding principle is that we want this condition to be satisfied. That's the that's the analogous thing that we had in the one jet case, where we had that X is an SRF if and only if J1F of X is an SR. That's the analogous statement. And then we basically just proceed iteratively. So if you give me a smooth map,
Hold on, sorry, just go. Okay. 1 second.
Yeah.
Okay.
Yeah. Okay. So again, I'm giving a bird's eye view of what the theory does, but so I will not actually explicitly construct these things because that would take us quite a bit far afield. But that's basically the main idea. And then you just proceed iteratively. So define a smooth map to be too generic. If the two-jet section of F intersects all of those things transversally, that would imply that all of these subsets are now submanifolds. So we can restrict along those and carry on this procedure. And so you can do that iteratively, like for any case. So Tom and Boardman constructed all of these submanifolds, and I think they also computed the relevant codimensions. So that's like it's a massive piece of work that went there. But just like for us, the upshot is that when you have a generic map to the plane, and here we are using Tom's jet transversality theorem to know that the collection of such maps is dense. But we basically have two kinds of singularities. One which is of, I guess, what we may call S1, 0 type, and these are the fault points. And locally, our fault points look like this map F. And the other type is the, I guess, S1, 1 type, which we refer to as the cusp points, and locally you get this description, at least when the source is two-dimensional. So that's that's what sort of, I'm not gonna prove in detail, but this is the thing that is quite important to us, because what we want to study at the end of the day is generic paths of smooth functions. And if you give me a path of smooth functions, I can think of it as a level preserving smooth map from n cross I to the plane. And so that's why looking at generic singularities to the plane is quite important. There is a bit of a caveat. I mean, it's, you have this condition, this level preserving condition, which doesn't show up directly in Tom Boardman theory. So you have to work a little bit harder if what you actually want to do is study generic paths of smooth functions. As far as I know, you don't get to directly input Tom Boardman theory. But again, it's one of those things that I will not go into details about. But I just wanted to give an overview what happens generically when the target is deflating.
That's very
Okay,
elegant.
thanks,
So at this point, you're pausing here, right? Because you've now proved something important, which is that generic maps of the plane have this local behavior. Either they don't have a critical point, or they have a critical point but they look locally like a fold, or they have a critical point and they look locally like a cusp.
Proved is a little bit of a strong word, but I've definitely announced that this is the case. Yeah. Are there any questions, comments, concerns, either online or in person? Give me a second. What time is it? So,
Filippos, just one question, if I may.
yes, Dario?
So if you go up a little bit to the condition x is an element of SRS of f, if and only if. Yeah, okay. No, sorry, actually just below that, we define a smooth map F to be too generic if it transversely intersects all those SRSs. And you said in this case, we know that the subsets actually turn out then to be submanifolds. Just remind me why that's the case.
Yeah, so that is the transversality. So you have this map J to F, which is from M to the second jet space.
Yeah.
And you have the SRSs are submanifolds here. And well, I guess the other way around, sorry. And so that's like, the general situation is if you have a smooth map from X to Y, and you have W a submanifold of Y, if F intersects W transversely, then F inverse of W is a submanifold of X.
Right. Yes. Okay.
So that's what we are using here. And
right.
And it means a submanifold, and you also know that the codimension of F inverse of W in X equals the codimension of W in Y.
Right. Yes. This is from lecture 2, right?
Yeah.
Okay. Yeah.
So for this to work, we do need to check that W is a submanifold of Y, right? So you do need to check that SRS is a submanifold of the jet space.
Yeah. No. There is a lot of work that you need to do. First of all, to define what the SRSs are as subsets, and then
isn't that a definition right there? I mean,
well, yeah, you could say so, but it's not a good. I feel like, I mean, so this is not a very good definition because the SRSs a priori do not depend on any smooth function F. You could say something along the lines of like define the SRSs such that this thing holds for all smooth functions F. I believe you could say that.
It's not very explicit,
but it's not very explicit, and I think the way one should do it is like define those explicitly and then check that whatever we defined gives you this as a property.
Okay.
But this is the guiding principle that will tell you that what you defined was the correct thing.
Good.
Because there's many things you could possibly define.
Yeah. But the weird thing is that as I'm learning, the jet bundle is constructed out of equivalence classes of functions anyway. You know, so although that definition sort of includes a function in it's not that far from definition. You know what I mean?
Yeah.
Because jet bundle is constructed out of as equivalence classes of functions.
True, but yeah, but this is a little bit yeah. That's fair. Okay. Yeah, I mean, the next thing that I want to talk a little bit about is maybe that's coming late into the series of talks, but just a coordinate independent definition of most critical points and CASP critical points. I mean, this isn't super important, but I think it's nice to kind of have. So I'll go through it a little bit quickly. So again, we concentrate on smooth functions whose target is R, and we have the set of critical points. We defined the Hessian already by going through a coordinate system. We could define the Hessian in a coordinate-dependent way. So we can define this map, which turns out to be a bilinear map from the tangent space, across the tangent space at P to R. And one way you can do it is that, well, if you give me two vectors in the tangent space, I can find a map from the plane to M that sends the origin to P. And also the partial derivatives at 0 give us the vectors that we began with. And one way that I can now define this bilinear pairing is if you give me those two vectors using gamma, I can evaluate the partial derivative of the composition f with gamma at x1 equals x2 equals 0. And there is something to check here. It's like an exercise in patience and the chain rule that this squared fp is well defined. I should say that's like quite crucially use the fact that p is a critical point to prove that this is well defined. So it's independent of gamma, and also you'll have to check this by passing to a coordinate system. You have to check that it's independent of gamma and independent of the coordinate system that you chose. And then this bilinear pairing is going to have a kernel, so it's going to be all of these vectors in the tangent space, such that they basically kill everything when it's paired with them. And so once you have this intrinsic sort of intrinsic Hessian, you can have an intrinsic third derivative map. So that would be a map going from the product of the kernel of the Hessian with itself 3 times to R. It's a case of trilinear pairing. And if you give me, it's basically the same formula. So you give me 3 vectors now in the kernel of the Hessian. I choose a map from R3 that sends the origin to P, and also the partial derivatives give us those vectors. And I define this trilinear pairing by evaluating the partial derivative of this composition when x1 equals x2 equals x3 equals 0, so at the origin. And again, you can show that this is well defined, so independent of eta by passing to a local channels. And so now if you want a coordinate independent definition for a Morse critical point, you would say that most critical point is, well, it's a critical point. And if I look at this intrinsic Hessian, its kernel has dimension 0. So it's like, so basically that's saying that the Hessian is non-singular.
I mean, we did have a coordinate definition yesterday already, saying that's transverse to the one jet.
Yeah, we did.
But this is going to be able to
for the CASP. Exactly. That's why I didn't introduce for the most critical points, but I think it helps more with the CASP.
Okay, this is nice.
And yeah, this is and I guess suggestively it came last in the course because it's probably my least favorite definition of a Morse critical point. I mean, it's good. It's cool. It's a cool one. But
I'd love to know what the fourth intrinsic Hessian is. How are you going to? Because each step you've got to sort of pump up a thing, right? You're gonna take the kernel of that guy.
I'm guessing that you have to take the kernel of that guy, and then you would have. I don't know. Like I have checked explicitly. I mean, if anyone wants to look at that and don't want to do it yourself, I can send it. I have checked explicitly the chain rule for the second intrinsic derivative.
Okay.
For the intrinsic Hessian.
Yeah.
I must confess that I haven't actually done the calculation.
No, that's great. That's important.
Yeah, but. Okay, so I'll give you the definition and also the example to keep in mind together. So the CASP, so a CASP critical point, if you give me a function, a real valued function, is going to be a critical point. Okay, it's no longer going to be a Morse type. So what's the like nicest way we can make it not be of Morse type? The kernel of the Hessian, I don't want it to be 0-dimensional anymore, so I will ask for it to be 1-dimensional. That's like the safest way. I can relax this condition. Well, okay, if it's 1-dimensional, then it must be generated by some vector in the tangent space of M at P. So let me just call this vector, like choose a vector that I'm calling V. And now I demand for V that the third intrinsic derivative evaluated at V, V is something that's non-zero. So just the example to keep in mind, and that's, well, really the only example needed to keep in mind, because everything would locally take this form, is a map from Rn+1 to R, where it has a cubic for the last coordinates, and then the rest coordinates take the form that we saw in the Morse case. They take this quadratic form. Like if you write down what the Hessian is for this, you would have and evaluate at 0, you would have like a 0 here, and then it would be -2, -2, 2, 2, blah, blah, blah. Okay. So it would be like the Hessian would have a 1-dimensional kernel, and the 3 here guarantees like this last condition. So because if we take the third derivative, that's going to be like the third derivative here evaluated at 0 will just be 6. So it will be something that's non-zero.
Is that the invariance of the critical points? I mean, so my question is, does every cusp point locally have, does the function can you find charts that it looks like that, or do you have to put a number in front of the x cubed?
So every simple cusp. So this, I think this condition is being a condition of being simple. And I believe that's true, yes. Every simple cusp would look like that, exactly.
Because like, for example, if I put like a 5 in front of the x cubed, then it's not, then you could obviously just change coordinates.
Well, you can change coordinates, yeah, exactly. And and you can even put a minus here, but again, you can change coordinates and be okay. So again, the only thing that you have to keep track of is the index. You again have an index, just like you did for the Morse critical points.
Yeah. It's interesting that there's no higher indices then, eh? But maybe if the dimension of the kernel was 2 or something, then there would be something interesting. Okay.
Well, what do you mean by interesting? What do you mean?
Like for a Morse critical point, like there is a number, an invariant number that you can attach it, like the number of +1s and -1s.
Yeah, you have it here as well.
So then you think when you go 1 higher,
Oh,
you'd think there'd be an index of that as well, but there isn't here. But maybe it's just because the kernel is one-dimensional. Maybe if the kernel is two-dimensional or something, then there would be. I don't know.
I'm not sure.
Yeah,
to
I'm
be
not
honest.
sure about
Yeah.
that. Okay. Yeah.
Okay. So this is a point where now we can start introducing Cerf paths. Um, do you think it's wise to do that now or take a break and do it afterwards? Because this is about the time
Let's
when I
take a
promised a break.
Yeah.
So let's take a break and then we're back in 10 minutes and we start talking about Cerf paths. So it's going to get, yeah, I think it will get nicer.
It's nice already.
Okay.
Okay.
And if you have any questions, either online or here, you can let me know anytime, but during the break as well. So I'll just mute.
Yeah, but it's my
Okay.
position.
Okay, I think we're back. Can you hear all right?
I can hear.
Okay, perfect. So perfect. So now I'll just start introducing the notion of surf paths. And I'll first start with a slightly, I guess, easier notion. Well, yes, they're not that different in complexity, but I'll first define what I'm calling pre-surf paths. This isn't very standard terminology, so you probably won't see them being called like that anywhere else, but it helps me.
Interject. As far as I understand it, the main and only main reference for this is still Cerf's paper, right?
So yeah. So it's Cerf's paper, and also so John Morgan has this like very beautiful lecture notes, and well, very beautiful lecture videos, and some of these videos come with lecture notes that I think are a very good reference, and I've like already like referenced them in previous. But also there, like he very much like Cerf's original work is the main input. It's just in English and I think like very well put together. Yeah. So now we are going to take again this space of smooth real value functions on M by F. Upper zero, we denote the subspace that consists of excellent Morse functions, which by now we know and love, and we know that this is an open and dense subset of F. And I will define two more subspaces now. So the first is F1 alpha. So F1 alpha is going to be a subspace of F, and it's going to consist of those smooth functions that have a single cusp critical point, like critical point of the form we basically just defined. And then all other critical points of F will be of Morse type. And also all critical values will have multiplicity 1. So I'm not going to have two critical points with the same critical value. So basically, like F1 alpha is the functions there are almost Morse functions, but they will have exactly one singularity of cusp type. Okay. And F1 beta. So F1 beta. Those are precisely the Morse functions that fail to be excellent Morse in the nicest possible way. So they have so these are all those functions which all their critical points are of Morse type, and they're going to have exactly one critical value with multiplicity 2. So exactly two critical points with the same critical value. Okay, that's F1 beta. And F1, I'll just be calling F1 the union of F1 alpha with F1 beta. So today we will exclusively deal with this subspace F0 union F1, which is a subspace of F. Okay, and here is like a little bit of a pictorial. I mean, so F0 union F1 it's what one may call a stratified space where F0 and F1 are the strata, and I mean, these are very infinite dimensional spaces, so you can't quite draw them in the two-dimensional plane, but just, I don't know, heuristically, maybe that's a picture that I will sometimes have in mind, where you have like a stratified space like F0 union F1 being this square, and then the F0 strata will come in connected components, and you will have this F1 strata like this shown. I mean, this is just a heuristic picture. There's nothing more into it, but So okay, so what is a pre-Cerf path in capital F? So I need to define a path in the space of smooth functions, and so that's going to be a smooth path. So in particular, a smooth map from R cross M to R. Notation wise, I'll sometimes call that capital F, which is, I guess, quite confusing because curly capital F is the space of all smooth real valued functions. So this isn't great notation, but then yeah, I would just denote like at time L the relevant smooth function to be F sub L. And I'm saying something that I will explain in pictures in a second, but I'm saying there is a discrete set of times. So you should think of these times as the times when the path hits F1. Okay. So there is a discrete set of times, Ti in a discrete set capital I, such that F sub lambda is an excellent Morse function for all lambda that don't live in this discrete set. F sub lambda hits F1 when at the chosen times lambda. And I have this extra condition here, which is that if you hit F1, if you are a smooth function in the path that hits F1, then there should exist a little epsilon, so that in that neighborhood of lambda, all the functions are in F0. I guess this condition is just a condition that my set Ti is discrete, so I haven't told you anything more. But also F sub lambda minus epsilon, F sub lambda plus epsilon must live in different connected components of F0. So just draw you examples of paths that are not allowed, and you see where this condition shows up. So this is an example of a path that is not allowed. So, okay, this is not allowed because this path crosses F1 not in like a discrete set of times, but in a continuous set of times. And then this path is also not allowed. This is the path that violates this last condition here, because no matter how close I look into this intersection, like all the points that are away from the intersection will be in the same connected components. So it's basically, like I have a path where I start with a Morse function, which is excellent Morse, and then at some point I hit F1, but then I change my mind and immediately go back, and I don't want to allow these things. So that's this condition here, and things that I allow are basically all things. Oops, sorry, are basically all things of this form.
Like your brown one was a little bit dramatic. Like it could be smooth. I mean, it could be because it
Well, but yeah. But these are, I mean, but remember, these are paths in the space of smooth functions. So they, I guess.
But in the heuristic picture.
Okay, the heuristic. That's right. Yeah. The heuristic picture. That's right. I agree, and I'll actually change that. Yeah. Here it's happening. Okay. Okay. And just as a remark, right, regarding terminology, so this F0 union F1, as we said, that's a codimension one stratified space. It basically means that there's just two strata. It means something more, but I don't want to go into the details of that. So I guess what I'm calling a pre-Cerf path here is what Cerf would call a good path in this codimension one stratified space. And whenever someone gives you a codimension one stratified space, you can write a notion of a path in it, which is like exactly this notion that I gave you here. Regardless of what the stratified space is, and you can call those to be the good paths. Yes. And also, Cerf would call what I'm calling a pre-Cerf path that only crosses F1 once. So the collection of discrete times is just a single point. He would call that a crossing path, but I want to reserve the term crossing path for something else. Like I want to reserve the term crossing path for paths that cross F1 beta. So I'm not going to do that. But if you do decide to read Cerf, just be aware of this. Now these aren't. Yeah, these are pre-Cerf paths. I promised you to define something that I'd call Cerf path. Well, before I do that, though, are there any questions or concerns? Take that as a no. So I defined for you what a CASP critical point is, and it defined what we'd be calling a birth depth critical point, which is very, very similar, but it's a specific type of a CASP critical point, but within a family. So if I take a smooth function which has a CASP critical point P0, let's say that V is a vector that generates the kernel of the intrinsic Hessian. I want to consider a smooth family, and I want to consider a smooth family. So that's a smooth path that contains my little f as f sub lambda 0. So like at time lambda 0, the relevant function in the family is f. Okay. So I have this condition here, which is well, it's basically the condition that I have drawn. If I look at so being a CASP critical point is only a condition. When I define a CASP critical point, I define it for maps to the real line. Okay. And I want a condition for how the path will generically behave when it crosses a CASP critical point. And I haven't given you anything to specify that yet. And that's that's the condition that I'm like writing down here. It's a condition that involves the partial derivative in the lambda direction. I haven't given you any such information yet, so I'm giving it now. So if I look at the partial derivative in the lambda direction, in the time direction for the path, and I look at it, so at time lambda 0, which is the time when the path crosses F1, this partial derivative at time lambda 0 itself is going to be a smooth real valued map, and its differential at the critical point evaluated at V must be non-zero. So let me just tell you what's an example. Sorry? Is there a question? No. So let me just tell you what basically just what's an example of something I want to exclude. Like I want to exclude a family that looks like this. If you look at this, in this description here, I have a lambda cubed. Well, if I take the partial derivative of this thing with respect to lambda, what will I be left with? I will be left with 3 lambda squared xn, and then if I take the differential of that and evaluate it at v, well, basically, if I take the differential of that at 0, that's going to be 0. The only way this would not be 0 is if I had this be like a lambda. So that's because then I would have the differential of that would be just 1 minus 1 of this. Is that clear? Yeah. So that's
very nice. Yeah.
that's an extra
Natural condition.
It's an extra generalistic condition
Yeah.
that we now input on paths.
Good. Good.
And a critical point, which is a cusp critical point that shows up in a path of smooth functions that further satisfies this generalistic condition is what we'll be referring to as a birth-death critical point. For the family, for the path. And the Cerf path is just a pre-Cerf path, which always satisfies this generalistic condition when this generalistic condition is relevant. So whenever a pre-Cerf path crosses the F1 alpha stratum, it must cross it in a generic way. So it must cross in a way that this condition is satisfied. Which in particular, sorry,
I'm listening to you.
Which in particular, you can, and I could just have given you like the coordinate definition. So like in particular, it's like, this is what all these paths must locally look like around the cusp. That's what this condition enforces. But I'm always a fan of like deriving the coordinate condition from something more invariant.
When you say which is generic in the above sense, but in the above sense you didn't use the word generic.
No, I'm being a little bit sloppy here,
okay.
but this is a generalistic condition.
Okay,
So this is a condition that you would get.
I see.
And you can make that actually precise.
Okay.
So if you do this whole like jet transversality business, you can have this be something that comes from a transversality condition to one of to a variant of this Tom Boardman strata that I.
So then instead paths would be open and dense in the space of.
So that's the. Okay. Yeah, I'm mentioning that explicitly somewhere, but yeah, that's exactly the point. So, and of course that is true for pre-Cerf paths as well, but Cerf paths have a more explicit like local description around the cusp critical points, which will be useful when manipulating things concretely. And it's always better when you can restrict things, the more you restrict them. Yeah, and yeah, I do actually, and you will see it. Gosh, I should have said that already. Why haven't I said that already? Because so if you actually look at this family here, sorry, this totally deserves an extra page. Yeah, so if you look at say this map, which takes the form. So we have f from Rn to R. Sorry, that's Rn cross R to R. And this is x1 up to xn comma t. So I'm taking this to be my time coordinates. And I have x1 cubed minus txn plus x1 squared. Well, I have some quadratic here. So what's going to happen is that if you look at for t less than 0, for t less than 0, this map has no critical points. It's like, you know, if you take the partial derivatives, right, that's going to be 3xn squared minus t. If you want to force that to be 0, you can't have it be 0 if t is less than 0. Okay. So for t less than 0, no critical points. For t equals 0, I have a CASP critical point. And for t greater than 0, well, if I want to force this to be 0, this is going to have two solutions. So I get two critical points, and they are of Morse type. That needs to be checked, but that's what's happening. So we have this path of functions, and this path starts with a function with no critical points. It gets to a CASP, and then the CASP gives birth to two critical points. So this is a path that gives birth to two critical points, and you can run this path backwards. So I could have a plus t here, so that would be running this path backwards, and there you would start with two critical points, and the CASP would kill them, and then you would have more critical points. So that's where the birth-death comes into play. And yeah, so a surf path that crosses f1 only once at the birth-death critical point is what we will be calling a birth-death path. So I mean, we will either call it a birth path or a death path depending on in which direction. But usually I will just say birth-death path and not choose a direction. And then a surf path that crosses f1 only once at f1 beta will be called a crossing path. And I should maybe say I should maybe also give an example for crossing path. Do I want to do that? I think I want to do that. Yeah, it's like, but I won't do it with. I won't do it with coordinates. So sorry, 1 second. I wanna. Okay. So I guess that's one picture, and then the other picture will be, well, symmetrically, but on the other side. apologies for my drawings, but here we have, so here the Morse functions that I am considering are just the height functions. And here I'm describing a path of Morse functions, which is it's this movie that takes the top critical point, bottom critical point, and passes them along.
Just show the critical points there.
Yeah. So this is critical point 1, this is critical point 2, and now this, well, let me actually do them with different colors. So now this critical point, which is green, now goes up here, and this critical point goes down here. There is this movie that you can see in your head, which just like swaps those two. And in the middle of this movie, you are going to have that those two critical points are at the same level, and that's where you have a non-excellent Morse function. So, and that's why sort of I like to call these like crossing paths, because that's like the critical values cross each other throughout this path. But this isn't standard. Cerf wouldn't call those crossing paths. How are we doing? Are there any questions, comments, concerns? We know what Cerf paths are, hopefully.
Yeah, I just enjoyed this this one that you draw, this diagram.
This one?
Kind of,
Yeah.
Yes.
Okay.
Me too.
Yeah. Because it's what he's telling you, that then this soft math part is that it's going to be related with the moving from this one to this one.
Yeah. I can. Would you like me to draw a relevant diagram for the CASP? Would that be? Yeah. Okay. If you enjoy, so here's what such a diagram would look like for the CASP. It's sorry. Okay, I don't know what that was. Again, I have my pair of copans. And again, I have two critical points. This one and this one. And again, my Morse functions are just the height functions for these surfaces. And so here I start with a Morse function with two critical points. And then I have this movie, which is like, it just progressively takes this bit and crashes it down. And so, but then the point at which those two die, that's the CASP point.
So then, which means then this one, like they're going to be rated if there's a soft part, if there's some soft part.
Yeah, well, I guess you're referring to the cobordism category. Yeah, exactly. So that's how you would get like this kind of relation in the cobordism category. Exactly. And you have also this kind of relation in the cobordism category again from here. Okay, and yeah, the thing that I do want to pitch is that, like, when working with these things, and that's what we will progressively start doing now, is like a very useful notion that's combinatorial in flavor. So it allows you to like draw pictures and understand a little bit more hands-on what's happening, is this notion of a Cerf graphic. So basically, if you give me a Cerf path, this Cerf path, I can always consider it to be a level-wise preserving map from R cross M to R cross R. And basically the Cerf graphic is going to consist of the collection of critical values, of like all critical values in R cross R. Okay, so let me just do this for like the examples that I gave you already. Like if I have the map, which is x cross t gets mapped to x squared cross t, sorry, comma t. Like what are all the critical values here? The critical values are like the locus of the critical values are all of the values of the form 0, t, right? So if this is so I get basically, I just get this line. This is what all the critical values of this map look like. Likewise, if I have the map x, t gets mapped to x cubed plus tx, t, then what are the critical values of that? Well, as we said, if t is less than 0, I have 2 critical points and therefore 2 critical values. And then as t goes closer to 0, those two come closer together and then they die at 0, and then I have no critical values afterwards. So this graphic of critical values would look like that. This is so this is a typical example of what the Cerf graphic for fold critical points looks like. This is a typical example for what the Cerf graphic of CASP critical points looks like. And then for a crossing, I gave instructions to myself here to draw a crossing example, but we already drew that. So so I'll just give you the graphic of it. And it's what does the graphic look like? I start with 2 critical values, say 0, 1. And then at some point they are at the same level. So that means that they become the same critical value. And then they split again. So so the graphic looks like this. Okay, so it's basically, I mean, locally it is the same as the graphic of a fold, because they are themselves like fold critical points. It's just that at some point the critical values, the 2 critical values become the same critical value, and they split again. Okay, and basically like any Cerf graphic that you give me is locally going to look like one of these 3 cases. So that's something that, you know, this is where it starts paying off, that we restrict our attention to Cerf paths, because like only so many things can happen at a Cerf path. You can either have like the S1, 0 critical points, which are the folds, or you can have the CASPs, or you can have like the crossings. That's all I can have. And that's so the theorem, which again we won't go, but it's basically the space of Cerf paths in F0 union F1 is going to be an open and dense subset of the space of all paths in F. So I can approximate any path of smooth function with a Cerf path. Now there's like there's 2 very useful theorems that Cerf proved, and this is where we are going to like get the connection back to the pseudo-isotopy theorem once I tell you what those theorems are. But are there any questions before I do so? We are doing well on time, so feel free to jump in and ask.
I have a sort of lingering question, which is just sort of relating what you've described here, which is the stratification of space of smooth functions, and describing Cerf paths between 2 points in that space and so on, and this Tom Boardman stratification that you were just describing an hour ago.
I have lingering questions about that myself.
Okay.
But
I haven't seen any explicit statements linking those two bodies of knowledge.
Yeah, it wasn't my intention to really link them. I think I just really wanted to talk a little bit about the Tom Boardman theory, because I think it's like it's an important thing to like at least be aware of. But I will agree with you that I would like to also myself see a more explicit link, and that goes to some things that we should talk more about. But I certainly don't fully have it on my head as clear as I wanted to be. Yeah, there is some link in that, like the Cerf paths are, you can think of them as special cases of like maps to the plane, right? Exactly. This level-wise preserved condition.
Exactly.
And the Tom Boardman theory tells you what maps to the plane generically look like.
Exactly.
It's just that the Tom Boardman theory itself, at least as I stated here, just doesn't take as an input this level-wise preserving condition. But there's definitely a link at that level.
Good. So,
Okay. Any other questions? So I can just tell you what those theorems say, and I will very much. I mean, again, main reference is Cerf's original, but also Jean Morgan's lecture notes. You can see proofs of them. So one theorem is the uniqueness of births, and the other theorem is the uniqueness of deaths. So what is uniqueness of births? So if you start with an excellent Morse function, and you have, say, alpha 1 up to alpha k are critical values of this excellent Morse function. So just like you have Cerf graphics, I sometimes like to write things down with like linear Cerf graphics. So I guess maybe you should call them like Morse graphics. I don't know, but I'm just thinking of the real line as this like perpendicular line, and I have a manifold n that maps into it, and I'm just recording the critical values here. So right, so what's the setup? The setup is if I have these critical values, and I consider the space of birth paths which begin at f, and the birth appears at a level between, say, alpha s and alpha s plus 1. That's just a subspace of all Cerf paths that I can write down. If the level sets, so you know, if you take any point t between alpha s and alpha s plus 1, since you are not crossing a critical value, that means that the topology of f inverse of t is not going to change throughout for any t throughout this interval. So I can just pick whichever t I want. And if the level sets,
importantly, it's also a manifold as well, because
by
definition, or not by
not by definition, but it's well,
because it's
you are submersion there.
It's a submersion.
Exactly. So if those level sets are connected, then the space of all of all such birth paths, like the space of all birth paths, where the birth appears at the level between alpha s and alpha s plus 1, is itself connected. It's a connected space. Okay. Yeah, we unfortunately we're not going to go into the proof. I mean, these are quite nice theorems that like Morgan has the proof, and it's a very beautiful argument, which just like we defined this surf paths, there is something that we may call elementary surf paths, which we could define. It's a very beautiful piece of work, and those elementary surf paths are quite geometric in nature, and so Cerf actually proves that the space of surf paths is well, he proves that like every surf path is homotopic to an elementary surf path, and then once you have that and you know what elementary surf paths are, it's actually quite easy to see that you would get as many connected components here as the connected components of the level sets. But anyway, that's not something that we're going to see. So I'm just putting out the theorem here. But are there any questions regarding the theorem? Like what it says. Okay. And then the uniqueness of deaths is if I give you again an excellence Morse function, but now I'm putting some restrictions, so I only consider manifolds W whose dimension is greater than or equal to 6. Okay. Now, if I take some integer I between 0 and n-1, and I have two critical points, ck and ck plus 1 of f, which are consecutive critical points. So here I'm like mapping their critical values. It's one after the other. And the critical points have index I and index I plus 1. Now, let's suppose that there exists a death path which starts at F and annihilates those two critical points. This assumption is sometimes referred to as those two critical points are in canceling position. And there is a geometric way to also translate this assumption to something very concrete. But let's just suppose that there exists one death path that starts at F and annihilates those critical points. And again, take some t in this interval. Now, if the level set is simply connected, again, we have a stronger condition than we did before. If the level set is simply connected, then the space of all death paths starting at F, which annihilate ck and ck plus 1, is connected.
Let me just say, I'm going to quibble here. T is in the vertical direction. You should give it a different name, shouldn't you? Y or something.
Yeah, that's.
Yes.
It's true that this t is not time. Yeah, I don't object that.
Okay, thank you.
So I should do that here as well. Okay. Yeah, I mean, the first thing that you might complain about is that.
Yeah, this is great. Before I complain,
Okay.
I'm not complaining. First of all, I'm not complaining. I just want you to go back to that picture that you drew earlier, and just
this picture.
Describe these concepts in this picture here, because we can see when this fails the conditions. But it's nice to see why it fails and so on.
Yes, that's a good point. I just don't know fully how to best do that. So for the, let me see how much space do I have here. Oh, I actually gave myself space. That's good. Copy paste. Yeah, so here, for example, if we look at the uniqueness of deaths, uniqueness of deaths theorem, you would have like this manifold on the left. That's our W, and the Morse function that we begin with is the height function, and so I have. So this is my height function, and I have my two critical values, and I'm calling those ck and ck plus 1. So that's ck, that's ck plus 1. This one is of index 1, and this one is of index 2. So we have two consecutive critical points, and they are of consecutive index. They are in canceling position, like I just described. Previously a certain path which annihilates those two critical points. And now if I look at some y here, so I look at some y here, I look at the pro image of this y. This is my wy, and the theorem says that if wy is simply connected, then the space of and w is greater than or equal to 6, then the space of all death paths that start from F and annihilate those two critical points is connected.
So it's not.
So what does that mean?
Yeah.
It means that if you give me any two death paths, I can find a homotopy between them. It's going to be a homotopy of death paths. That's what it basically means, like in very quick ways. I can't. Yeah.
And maybe you can even draw it in that picture where you had that heuristic picture of F1. You could give sort of two examples of those parts, and then say, well, you can actually then.
Which picture are you referring to?
You had the picture of the stratification of F.
Yeah. I can do that. Yeah. I had like. Yeah, that's actually a good point. Yeah. So this is F0, F0, F1 alpha, and now this is a connect component which consists of functions with two critical points. And this is a connect component which consists of Morse functions with 0 critical points. I could have said, I don't know, like n and n plus 2, but it doesn't matter. And so if this is my point f, this is the function that I start with. It's a function with say 2 critical points that are consecutive and have consecutive index. What I'm saying is that if there exists a Cerf path like that, then the space of all Cerf paths like that, I don't know, you can draw whichever one you want, is connected. like I don't have, you know, I don't have a gap somewhere here.
That's right. Yeah, that's right. Is that clear?
And yeah, the remaining time, I would just tell you how to like now recast the pseudo-isotopy theory like in this sort of language, and how to like start thinking about it a little bit. But before that, questions, comments, concerns. So now I don't know if anyone remembers the pseudo-isotopy theory, or if anyone remembers how we sort of like recast it into this language of smooth functions. But the only thing that maybe I should say is like recall. So our objective. So I had given you an argument that resulted in our objective being to calculate pi1 of f comma f. So I guess we start with a manifold M, and I somehow gave you an argument that said that if you want to prove that every pseudo-isotopy on M is isotopic to an isotopy, what you should try to prove is that this relevant fundamental group is trivial. Exactly. Right. So in particular, what that means is if you give me a function, so say, I don't know, so f0 and f1, or maybe.
Sorry, what was this space? Epsilon of M.
Yeah, I will. Yeah. So this is the space of all smooth real valued functions on M cross I with no critical points. Okay. Yeah. So the picture. So basically, so what would we have to prove? So if you give me f0 and f1, and those are smooth real valued functions on M cross I with no critical points, and you give me a path between them in the space of all smooth real valued functions, I want to find a homotopy to another path of smooth real valued functions that have no critical points. Okay. Bruce, your Mac will sleep soon if it's not put into power. Okay, is it clear what we're trying to do? So, okay, so now what is, so okay, so if you give me a path in the space of all smooth real valued functions on M cross I by Cerf's theory, I can homotop it, I can perturb it a little bit to a Cerf path. So I can always find the Cerf path, but will go from f0 to f1. Okay. What is, so if f0 has no critical points, then I don't know, its Morse graphic would look like that. It's going to have no critical values. For f1, its Morse graphic is going to look like that. It's going to have no critical values. Okay. What is a potential Cerf graphic? between those things. I mean, a potential surf graphic. So what would be a surf graphic? That would be just, oh, I defined what a surf graphic was. Yeah. So what's a potential surf graphic between these things? It could be very complicated. Like it could be, I don't know, like I could have some kind of birth, maybe another kind of birth, maybe a crossing here, and maybe like, sorry, maybe those things die here, and maybe those things die here.
It's complicated, but it's only births and crossings.
It's only births,
yeah, that's all.
Yeah, that's all. But it could be just very, very convoluted. Okay. And so that would be like the surf graphic for a surf path from F0 to F1. Now, if this path happened to be a path of functions with no critical points, then the surf graphic would be extremely simple. It would be just,
maybe just label each of those lines with F0 and F1.
okay. So that's like, I don't know, like surf graphic 1. Surf graphic 2. So at least pictorially, what I want to do if I want to prove the pseudo-isotopy theorem is I want to show that, like, if you give me any surf graphic, I can turn it into the empty surf graphic. If I can do that for a given manifold M, then I have shown that the pseudo-isotopy theorem holds. That's basically the strategy in pictorial terms. And you can see, maybe you can start seeing where these uniqueness of births and uniqueness of deaths theorems come into play, because here is like one example where I can have a birth followed by a death. So so this here is F0 M cross I to R, F1 M cross I to R. Okay. And I don't know, maybe I'll also tell you to keep track of F2, which is an intermediate Morse function. Okay, so this is a potential surf graphic. And if I want to argue that this surf graphic is equivalent to an empty surf graphic, what would I have to look at? So if you look at like this Morse function in the middle, which I have labeled as pink, it has those two critical points, and those two critical points here, this is a death path. Okay. Well, there is another death path that I can write. I can write the inverse of this birth path. The inverse of this birth path and this death path must be connected via homotopy. That's if the conditions of this uniqueness of deaths theorem is satisfied. So if those conditions are satisfied, then the path which is described here is homotopic to a path which is a given birth followed by its inverse. Birth followed by its inverse, like any path followed by its inverse, is homotopic to the constant map, to the constant path, the identity, and that has empty surf graphic. So this is where like those theorems of like uniqueness of births and uniqueness of deaths come into play. We have load shedding here, but I don't know if you can still hear us.
Yes, I can still hear you.
Okay. Okay, great. So that's yeah, I think that's what I wanted to say for today. I mean, we're also exactly 4 p.m. So perfect timing. It was organized. Yeah. So yeah. So please ask questions. But I won't say anything more. So next time, I will tell you about F2. So we construct F0 and F1. So next time I'll tell you about F2, which is where you have like this is the stratum of the space of all smooth real valued functions that you need if you want to study generic 2-parameter families. And I'll like basically the next 2 lectures we'll just go through more cases of simplifying Surf graphics. We're not going to go through the entire argument where you just simplify everything, but my hope is to give you like as many examples of simplifying Surf graphics as possible in the remaining time. So that's where we are headed.
But are we going to finally come to this last argument that we had,
which
to prove the fundamental group of this?
I will give you. I will try to give you as much of a detailed sketch as possible. I will reduce it to a statement that I don't think I will have time to prove. But unfortunately, but hopefully I'll reduce it to a statement that will make it at least believable. And we can talk. I mean, we can have to talk more about it.
Yeah, because it seems like I didn't understand clear like this last part, but that's why I was hoping maybe like you can do it in the next thing in the next talk or something.
Yeah, well, the next talks. So this one, yeah, here I just try to sketch an argument a little bit as to how these theorems are useful. But we are going to see this like example again, basically, and we're going to see like similar theorems again and how they are used to. Basically, all I want is for you to be happy that it's somehow important related to the pseudo-isotopy theorem to be able to simplify Surf graphics. So if you're happy that this is like sort of like useful to be able to simplify Surf graphics, that's important. And then those theorems give us ways to simplify Surf graphics. And we're going to see that again, and we're going to see more ways to simplify Surf graphics later on. But that's
It's very cool. Thank you. Very clear. Thank you.
Yeah, thank you.
Ken and Dario, any comments? Yeah, Ken.
No, I just wanted to say that was excellent. Very clear all the way through.
Oh, thank you very much, Ken. Thank you so much for coming as well. Being here, yeah.
Yeah, next week, Tuesday, we've got our next lecture. Wednesday.
Yeah, it's Wednesday, Thursday, right?
Yeah. I'm getting a job interview on Wednesday, so I might not be here, but
oh, no.
I will be.
I want you here.
Okay, maybe we can. Absolutely, we can maybe reschedule.
Yeah, let's do it on Tuesday. Like if the NITheCS people are okay with it, do you think it will be possible?
I mean, I think the best alternative is just to postpone the entire thing by a week.
Oh, I'd be happy with that.
Okay. Both Wednesday and the Thursday lectures. Okay. You know what I mean?
Are they going to be okay with that though?
Yeah, I think so. Because we're all friends here. But we'll chat to them. Yeah. Let me say if I understand something correctly. So if you just scroll down to the end now, so we're trying to simplify these Surf graphics.
Yeah.
So my understanding here is that you have to go. You have to see. Okay. Okay, just a second. My understanding is that you've described this beautifully, how we're going to be able to solve the pseudo-isotopy problem by simplifying the surf graphics. As far as if you might say at the moment we're just dealing with F0 and F1, that's stratification, and next time you're going to talk about F2. But we're at this level already, just knowing about F0 and F1, you've already shown that under nice conditions we can simplify the surf graphic. So am I right in thinking that we only need to study F2 to make sure that we can simplify, it'll give us conditions under which we can simplify the surf graphics, even under better than what we currently have. You know what I mean? Because what we currently have is only under very strict conditions, sort of simply connected power, and then you can do this.
No.
But
So see, what we currently have, no. So F2 is not going to be able to relax those conditions.
yeah.
So, because if you remember, Cerf only proved the pseudo-isotopy
Yes.
theorem under conditions.
Yes.
What were the conditions?
Yeah.
They were like the dimension of M has to be greater or equal to 5.
Yeah.
And M has to be simply connected.
Okay.
Which is what shows up here. I mean,
Yes.
see, I told you in the uniqueness of depths theorem, I want the dimension of the cobordism to be greater or equal to 6.
Yeah.
Well, what's W? W is just M cross I, so that's the dimension of M has to be greater or equal to 5. And M being simply connected would imply that the level sets here are simply connected. So it's not the case that F2 will be able to relax those conditions, but F2 will be able to.
What's it going to buy us?
It's going to buy us the ability to simplify more complicated graphics than the one I just gave you. Because here is an example.
I see.
I mean, and I'm like okay, here is an example of a graphic that which you know and love.
Right. Let's see. I should know these things, but I need to be reminded of them.
I mean, my drawings are horrible, but you basically see. So here, like, in order to simplify this, like, we need to do a swallowtail in this part, and then once you have a swallowtail in this part, you then use uniqueness of depths in this part. So there are just much more complicated surf graphics than the one I gave you, and I only gave you this example sort of to illustrate where these theorems of uniqueness of births and uniqueness of deaths gets used. But you need more. You don't need to know that you don't need to know the thing that I promised in the beginning, which is the space of, I guess, what I would call surf 2 paths is open and dense. Like, you don't need to know that any homotopy between surf paths is a homotopy that passes through F2. You basically just need to know, you just need to like identify some homotopies of surf paths that are enough for your purposes. Your purposes being simplifying the surf graphics. So the swallowtail is one of them. I mean, you basically end up using like all of them, but you don't need to. So crucially, like, Cerf didn't have to prove that any homotopy between surf paths is what I would call a surf 2 path.
That's right, because he just wanted to simplify the graphic.
He didn't
want to classify the ways in which he could simplify the graphic.
Exactly.
I see.
Which is something that
that's something you have to worry about.
Exactly.
I see. Okay.
Okay. It does turn out that, I mean,
I see.